are some pictures I created using MATLAB of these particular surfaces. Okay. Now, if I actually have the MATLAB running, I could pick it up and turn it around, you know, like you did in Maple the other day. So z equals x squared plus y squared. I guess one nice thing to do, you know, is to zero out one of the variables, right? So if I get rid of the y and just have z equals x squared, it's a parabola. So same thing if I get rid of the x. So this is a paraboloid, I guess. And then how about the next one? Sure, it's opening downward, right? So it's a paraboloid also. And then for those of you that were thinking about the last one here, yeah, good question. That's a good question. But that's a beautiful picture right there. Z equals y squared minus x squared. And I think what we're going to do is we're going to, well, take some partial derivatives of these three particular functions and learn what we learned today and see what happens. So what are partial derivatives? Well, it's the equivalent of a derivative in Calc 1 for multivariable functions. Of course, these are functions of two variables. Z is a function of x and y in all three of these examples. Why are these like this, you mean? Let's see. Yeah, kind of. I think that, do I have a good reason that it's like that? Well, that's exactly what you do is you specify what you're going to put in for x and y. And I specified it looks like from, I don't know, -3 to +3 here. Okay? Yeah. But if you think about it, where is z going to be the largest on that box? In the corners, right? Like 3, 3, the output's 18. So it's really high. Whereas if I'm at 3, 0, the output's only 9. So you are going to get that kind of look for any particular square where you might cut it off. Thanks, Brianne. See ya. So oh, probably. I didn't write the software. I don't know. I mean, yeah, good question. I don't know. So you could see? Yeah, maybe. Well, anyways, let's go to work. Let's do that. So here, I'm going to start your PowerPoint here on partial derivatives. And I decided to start with something right from the book, and that's notation for first partial derivatives. Maybe I should have done this with my Calc 1 students because they had a real tough time the other day because I had been talking about f prime of x, right? And they understood that. They had a nice definition for that. And all of a sudden I started saying df dx or d dx of f of x. And I hadn't explained it yet, right? So then I went into, okay, here's Newton and here's Leibniz. And then I talked about that this is a really nice notation for lots of reasons, actually one of which we'll get to today. But this is nice because in some ways this tells you that a derivative is a rate of change, right? And the units are whatever f is over whatever x is. Miles per hour, feet per second. In our example, it was bowling alleys closing per month. Okay, but that's what it was. All right. So here, for z as a function of x and y, the partial derivatives, now notice how they write this. F with a little x and f with a little y. There are two different partial derivatives if your function has two variables. notice right here, curly D's, I call them. Curly D's. They look like this. When you see that curly D, that tells you you have a partial derivative. There will be times in your mathematical career when you will have partial derivatives and regular derivatives in the same equation. So I'm telling you right now, pay attention to curly being partial. The way I would read this is the partial derivative with respect to x of f of xy. That's the same thing as this. Oh, and then because we've been using z as a function of x and y, you really want to shorthand, just write z sub x, or partial z with respect to x. Okay, so there's a lot of ways to write it, and I want to point that out before I go anywhere. You guys follow that? Once you've computed a partial derivative, just like a regular derivative, you might want to evaluate it at some point, right? Like, I'll tell you, in my class, we had to find f prime of 3. Why? Well, what might f prime of 3 give you in Calc 1? It's a constant, but why do you think they wanted to compute it? It was the slope of the tangent line at the point 3 comma whatever it was. Okay? So that's what they wanted it for. Well, you could do the same thing with partial derivatives. You can evaluate them at a point, but you'll need to have 2 inputs, right? If it's a function of 2 variables. So you could evaluate fx of a comma b. Right? So I could find the partial derivative at the point 0, 0, or the partial derivative at the point 1 comma 1, etc. Does that make sense? Now, this notation, I don't know that you're familiar with, because I don't think my students are. But it's the Leibniz notation. Like if I have df dx, and I want to evaluate it at x equals 3, what people do is they draw a bar, and at the bottom they put x equals 3. That's the same thing as f prime of 3. I guess so. We put that bar when we're evaluating an integral. Yeah. I don't know the relationship between the two, but you're right. You're right. Good point. That's a good thing to recognize. So anyways, there's your notation. Explained as well as I think we need to. Okay. Here's your picture. So we have a function of 2 variables. And, you know, it's a surface. This red thing is the picture. That's the surface. So this is a graph of z is a function of x and y. Right? So it could be a paraboloid, for instance. And, you know, here is a point, x naught, y naught, z naught. And so when you compute df dx, the partial with respect to x, first of all, the idea is you treat y, or all other variables, as constants. That's the idea. You treat y as a constant. Okay? So I should show you an example maybe in a second. Yeah, let's do one. Give me the ugliest function of x and y you can. Go ahead. Come on, I just gave you an exam. Be merciless. Come on. X to the 5/6 power. Y cubed. That's it?
Plus I sine of x, y.
plus the sine of xy cubed. Was it x and then the y is cubed, or is the whole thing cubed?
Sine of quantity xy cubed.
Okay, so this, to be precise, divided by, thanks a lot. 4 you said? Oh, that was really nice. Okay, so now, okay, so fx, the partial derivative of xy. It's going to be much easier than you think. Now, first of all, I factor out that 1/4 that someone, I don't know why he said divide by 4. But that's a constant, so I don't have to worry about that. So now, what's left? Well, I treat y cubed as a constant. So I'm just going to bring down y cubed. So I'm going to get, bing, 5/6, bing, x to the what? Negative 1/6 y cubed. There's no bong, because the bong is 1. Plus, well, I'm going to get cosine of xy cubed. And now I have to be careful. I have to multiply that cosine by something. No, because the x is also being cubed. See that? Someone wasn't as nice as that. So let's see. So what goes here? 3 xy squared. Do I really want to do it that way? No. I'd probably simplify. The fact that I have x cubed, y cubed is what I really have. So yeah, what goes there is I have a y cubed and I have a 3x squared. That's how I'd write it. Okay. So that the process of taking partial derivatives isn't that bad. As long as you can keep people that want to give you a bad denominator out of the picture. Okay. But do you guys get the process? Now what are we really doing? We're treating y as a constant. This picture shows you what you're doing. See? Y equals y naught. And why not? Right? Y is a constant. So if it's this constant, then I'm in this plane, this blue plane. Well, if I'm in this blue plane, what's the intersection of the surface with that blue plane? It's that black curve. So if you think about what you're doing, you're finding the derivative with respect to x of that curve. And so you're finding the slope of the tangent line if you evaluate it at a particular point. Now the only thing that's weird about this is that who's to say that that's the constant I'm talking about? Maybe I'm talking about a different constant. Well, then you'd have a different blue plane over here. And you'd have a different black curve over here. And you'd have a different tangent line, right? Do you understand? Somehow this accomplishes all of that. Because you can evaluate this partial derivative. See, this partial derivative is also a function of x and y. And so you can evaluate it at any particular x and y. And when you picked that point, what you did was you fixed the plane, you found the curve, you found the tangent line to that curve. Does that make sense? Cool. Okay, now. Oh, yeah. Definition. This was in your book. I was trying to decide what to show you. So, how's that look for a definition? Kind of. It was pretty much that. When we studied vector-valued functions, and we had r of x, and then we said, let's do r prime of x, right? We said, okay, let's think about what that means. Well, in this particular example, notice what I'm doing. When I say partial with respect to x, in other words, this is df dx, okay? Notice the only place that the delta x is showing up is in the first coordinate, not in the second, right? Because we're treating the second one as a constant. So, you know, that's a very nice definition that should make sense to you at this point. Clayton?
When you start having more than two variables, you just keep running them up to the right.
Sure. So let's suppose I have w is a function of x, y, and z. And actually your book talks about this. I didn't put it on the slides because I thought it's the same thing. I can talk about dw dx or dw dy or partial w with respect to z.
You just
Treat the others as constants. Absolutely. As long as you want. Sure. As many variables as you need. Found it? What page?
3.2, 904.
Page 904. Let's see. 13.2. Yeah, we just had this. Let's see. Ha ha. Those are partial derivatives. That's what you're doing there. Yeah, so we already hinted at, hey, this is important. Okay. Cool. It says it represents the slope of this curve at the point x naught, y naught, f of x naught, y naught. Remember, that's z. Naught. Notice that both the curve and the tangent line lie in the... Yeah, okay, we already said that. Let's get out of here. I did include it, after all. You could do this. Well, no, this is df dy, right? Same idea, different direction. Okay, moving on. Let's do some examples here. And then I have a group work, which will be fun. So, let's look at the ones we were working on. So let's take z equals x squared plus y squared. And we have z equals 1 minus x squared minus y squared. And we have z equals y squared minus x squared. And these are very simple examples, but go ahead and find both partial derivatives, zx and zy, for each of these. I'll pause while you're working. So there's some answers for you, right? If you're treating the y's as constant, then because they're just added on, derivative of a constant is 0, so they kind of go away. Do you see that? If you treat x as constant, well then that x squared is a constant, so that goes away. So there they are, partial derivatives for these three functions. I guess these are very simple examples. Okay. So we'll come back to, well, okay, I'll throw it out there now. Your book is interesting to me because they teach you what partial derivatives are, and then they do another section, and then finally they come back and they say, what are they good for? And I don't tend to operate that way. I want to know what's it good for as soon as I have to do any work with it. I don't know. That's how I work. Idea what they might be good for? Partial derivatives? Tangent lines? Yep. Of course, what do you mean by that? Here, let me show you why I asked that question. If I go back to my picture of these functions, and I say I want a tangent line at that point, which tangent line? How many tangent lines are there at that point? Infinitely many. So there's a tangent plane at that point. Yeah. Formed by all the tangent lines at that point. That's a good question. Well, what would I need to find a tangent plane? That's a good question. How? Yeah. I guess I don't see how you have a plane if I have a point. Can you explain that? I have a line. Okay. I do have, in a sense, a particular tangent line, right? That was the picture I showed you. Let me go back. When I find a partial derivative, let's see. I know where it is. It's right back here. Yeah, there it is. When I find df dy, I have a particular tangent line, right? The tangent line's in this plane. Oh, okay. So now that's a question. Will df dy be perpendicular to df dx? That's not quite right. Will the tangent line that I draw here in blue be perpendicular to the tangent line I drew in blue the other time? Remember, the other one I did was I fixed a plane y equals y naught. Now, what'd that look like? I guess it looked kind of like this, right? Remember this on the other slide? And so we said the intersection of the surface there is a curve. And so if I drew the tangent line, there it is. And is that tangent line perpendicular to this tangent line? I guess so. And now do I get a tangent plane from those two tangent lines? Well, I guess so, because any other tangent line would be in the plane that those two are in. Why do you say that? Here, I guess to answer that question, here's a question. Hold up a line up in the air. Okay. How many lines are perpendicular to that line? Infinitely many. Not just one. Right? So, I guess I would argue that these two tangent lines are perpendicular, even if they're not maybe what you want. But they are perpendicular. All right. The slope of the plane? What do you mean?
Like, if you really, if you didn't have the function on,
Uh-huh.
could you graph the function?
The tangent plane?
Yeah.
Which I still haven't graphed yet, right? I mean, the tangent plane, I'm saying, is the plane that contains this blue line and that black line. Which, by the way, we're not going to cover for sections yet, okay? But we will get there. That tangent plane, you have to remember how you graph a plane, or how you write the equation of a plane. Do you guys know the equation of a plane? Yeah, you need the normal vector, because it's a x minus x naught plus b y minus y naught, nice curly Q, plus c z minus z naught is 0, where a, b, c, that's the normal vector, okay? And yes, we can do things like this, and we're getting there. It's going to take a little time. The partial derivatives are going to give me the normal vector eventually. No, that's good. That's good, though. Okay, but let's move on. What else can I do with these guys? Well, we'll come back. Ah! What? What about wave functions? Talk to me before I throw this up there. wave equation, or the heat equation also, right? Heat equation. These guys are what are known as partial differential. Let me undo that somehow. Partial differential equations. Which is not what we study here when we teach our differential equations. You guys next would probably take a course in ordinary diff EQ, ordinary differential equations. In other words, we get differential equations from good old ddx, dy dx. Okay, actually, my Calc 2 people, I think you saw just a few of these differential equations, very few. Those are called ordinary. But you can also do work with differential equations with partial. I guess I would write df dx and df dy. And yes, these very famous differential equations that govern some very important processes that we want to learn about are partial differential equations. Okay? That was worth talking about, I think. All right. How about this? Higher order partial derivatives, right? Basically, what am I doing here? I'm doing what I did in Calc 1 when I told them how to take y double prime, the second derivative. Now, why are there 4 of them? Yeah. Each one of those, you could take the x derivative of or the y derivative of, right? Here's df dx. I could take its partial with respect to x, or I could take its partial with respect to y. Now, we know in Calc 1, what's the second derivative tell you? First derivative gives me slope of the tangent. What's the second derivative give me? What is it? Concavity, right. So in Calc 2, well, the second derivatives are going to be helpful also. I guess that's all we say so far, that they're going to be helpful. Steve?
What happens if you like do the partial derivative of with respect to y, and then you just do it with respect to x on that one?
That's this, right? So here it is. That's one of these guys. Here's the partial derivative with respect to y. Now I'm going to take the partial derivative with respect to x of it. That's right. So that would be d squared f dx dy. Oh, that's ugly. I like this notation right here.
What's the point of it?
Well, okay, yeah. Why are we doing this? Why did we do it in Calc 1? What?
I mean, like specifically you're taking like the x like the y one.
Okay. I'm going to go back to Calc 1. I understand your question. You're saying, I can imagine doing 2 x's in a row, but you can't imagine doing an x and then a y. But it turns out it's going to give me valuable information. Just like this did. Here, let's talk about what kind of information we got from y double prime. When did you need y double prime? Do you know? Relative min and max, right. Because how did you find a relative min or max? You set y prime equal to 0 and you solve. And then you get some solutions. But just because you have those solutions doesn't mean you know if they're maxes or mins or maybe neither, right? Like in the cubed example, there was neither. So then what you do is if you have a solution, you evaluate the second derivative of that. Okay, and that told me max or min, or else I'm not sure. You guys follow that? Well, it could be an inflection point, or it could be, yeah, possible inflection point. So it's going to be the same game here. I'm going to set first derivatives equal to 0. Okay? And solve. And I'll get what are called critical points. Matter of fact, we're about to do that. Let's go do that. Let's go back to our example. Wait for what? Oh, this. Here, I'll pause. Well, okay. So what are we going to do? I don't know. Well, okay. All three of these functions have exactly one critical point, right? Critical point isn't even defined in the section we're covering today, but you know what it is, so I thought, let's show you. At where? 0, 0. That's the only way to get these partial derivatives equal to 0. Now we'll talk about more precisely what exactly I mean by a critical point. But once you have a critical point, what does that tell you in Calc 1? Well, you might have a max or a min, or an either. Let's go back to our pictures. So where's our pictures? Boom. Well, this critical point is a what? Min. The first one's a min. The second one? Max. And the third one? That's what I call a saddle point. Doesn't it? Why is it a... So is it a max or a min? No. Well, kind of both. Okay, that's what I want to hear, right? If I fix a plane here, I could see that it's a max of that parabola. But if I fix a plane here, I could see it's a min of this parabola. Right? That's what you call a saddle point, because you can imagine just going for a ride, right? Okay, so put that away. Should I do this part yet? What time is it? 10 minutes, break time. All right. Let's take our break. We'll come back, and by then I'll have figured out what I want to do.